Welcome to Lecture 11 of the Wireless Communications course at Chalmers University of Technology. My name is Henk Wemiers. In this lecture, we move away from the textbook and look at more current topics. We'll focus on 5G, in particular looking at the key technologies, at MIMO Capacity, multi-user MIMO, and finally Massive MIMO. The lecture is based in part on the book, but also on the following papers. First of all, 5G, a tutorial overview of standards, trials, challenges, deployment, and practice by Mansour Shafi et al. An overview of Massive MIMO, benefits and challenges by Lulu et al. And Massive MIMO, 10 myths and 1 critical question by Emil Bjornsen et al. The learning outcomes for today are the following. You should be able to describe the key characteristics of 5G, difference between single-user and multi-user MIMO, express multi-user MIMO and uplink and downlink as a standard MIMO problem, explain what is Massive MIMO and why it is beneficial in terms of orthogonal channels, and also describe what is pilot contamination. Last time we focused mainly on the narrowband MIMO model. It's given by the expression on the top, where H is a channel matrix. This is a complex matrix of size MR by MT, where MR is the number of receive antennas, MT the number of transmit antennas. When the receiver has an estimate of the channel H, it can perform different detectors, such as maximum likelihood, zero forcing, or MMSE. Maximum likelihood is the optimal detector. It requires searching over all possible X values that could have been transmitted and is thus exponential in the number of transmit antennas. Zero forcing tries to invert the channel. However, this fails when the channel is poorly conditioned, as the inversion leads to noise enhancement. Finally, MMSE tries to approximately invert the channel and thus reduce noise enhancement. When channel state information is available at the transmitter, we can do much more. We can use a singular value decomposition to create parallel non-interfering streams. The expression for the singular value decomposition is shown here, where U and V are unitary matrices, and sigma is the matrix of singular values. Sigma is a diagonal matrix, where all the entries on the diagonal are non-negative. The figure below shows how we use the SVD. What we do is we take our data symbols, x tilde, we precode them with V. This then gives us the signals that we will transmit over the channel. We apply them to the channel H, we receive an observation Y, and then we apply a so-called shaping transformation to have our final observation X tilde, Y tilde. We see that Y tilde can be related to X tilde using the concatenation of these matrices. We can substitute H for its singular value decomposition. This is shown here. Now, since U and V are unitary, U Hermitian U is an identity, as is V Hermitian V. This means that Y tilde is a diagonal matrix times X tilde plus noise. In more detail, sigma is the matrix of singular values. It's a diagonal matrix with these entries. These entries are by convention ordered from largest to smallest. They are all non-negative. The final entry here, sigma RH, that is non-zero, has this subscript RH, which is the rank of the channel. The rank of the channel is always less or equal than the minimum of the number of transmit and receive antennas. We look now in more detail what is Y tilde. We see that Y tilde K, so the kth entry in Y tilde, can be written as sigma K, the kth entry in the matrix of singular values, times X tilde K plus noise. This is true for any K ranging from 1 to the minimum of MT and MR. However, when K is greater or equal than RH, sigma will be 0, so basically on those streams you only observe noise. This means that the size of X tilde is limited to RH. It does not make sense to make X tilde longer than RH. As an extreme case, one could choose to make X tilde of length 1, and this is called beamforming. In that case, we only send our information over one stream using the largest singular value. We also briefly talked about MIMO in the wideband regime. In that case, we would combine MIMO with OFDM, using OFDM transmitters and receivers. If we then look at any given subcarrier, we have again a narrowband MIMO model. So Zk is now the observation on subcarrier K. Hk is the channel matrix on subcarrier K. Hk is again of size mr by mt. In contrast to 4G, which is mainly focused on providing high data rates, this is just one of the application scenarios for 5G, so-called massive broadband. Massive broadband involves very high peak data rates, as well as very high rates whenever it is needed. We will also support many more devices and much more traffic. However, massive broadband is just one of the areas. There is also two others. One is massive machine-type communication, for instance for sensor networks and Internet of Things. Here the focus is also on having many more devices, but more specifically on low power consumption. A third application scenario is critical machine-type communication. Here our focus is on reliability and latency. This can include applications such as virtual reality and autonomous driving. The requirements and use cases are here in this table described in more detail. So again, there are three main use cases: enhanced mobile broadband, ultra-reliable low latency communication, and massive machine-type communication for Internet of Things. It is important to note that the requirements are very challenging depending on the application. So for enhanced mobile broadband, we can have downlink data rates of up to 20 gigabits per second. For ultra-reliable low latency communication, we can have latencies of about 1 millisecond, which is much less than current latencies. For Internet of Things, massive machine-type communication, we can have many devices per square kilometer. We will also be able to deal with very high velocities of the users, very large bandwidths, up to 1 gigahertz, and very low error probabilities. In order to meet those very demanding requirements, 5G will rely on a number of technological enablers. It will use much more bandwidth than before by going to higher carrier frequencies above 24 GHz, where multiple gigahertz of bandwidth can be made available. This is so-called millimeter wave. Secondly, we'll use more antennas. So rather than a base station having just a few antennas, it can have hundreds of antennas. This is called massive MIMO, and this will be the main topic of today's lecture. We will also have many more base stations. So there are shorter distances between the users and the base stations. This leads to so-called femtocells. We will also design new kind of signals and new kind of codes, for instance for short packet transmission and things such as polar codes. Finally, there will be many other technological enablers such as device-to-device communication and network slicing. In order to understand massive MIMO, we should first look into multi-user MIMO. In order to understand multi-user MIMO, it is worth to look back to the MIMO capacity. This slide provides an overview of the capacity for the narrowband MIMO system for a given channel. The observation model is shown by the first bullet, where we have a certain covariance matrix of the transmitted signal and a certain transmit power. The channel can be decomposed using a singular value decomposition, where sigma is the matrix containing the singular values along the diagonal. We accept without proof that the channel capacity of a MIMO system for a fixed channel is given by the following expression. B is the bandwidth, H is the channel, R is the transmit covariance, and again we enforce a certain transmit power. If we have one transmit and one receive antenna, this expression reverts to the standard single input, single output channel capacity. We now look at two different cases. First of all, when the channel is not known to the transmitter. In that case, the only covariance matrix that makes sense is a scaled identity matrix. We just split the total available power across all the transmit antennas. We can substitute back this expression here and make use of the fact that H times H Hermitian can be written like this. In the end, we find the following expression of the capacity. We can now pull out U Hermitian and U to the left and the right hand side. These are just unitary transformations, so they don't affect the identity matrix, which allows us then to write the capacity as the bandwidth times the log of the determinant of this matrix here. So note that the U Hermitian and U are gone. This overall matrix is diagonal because the identity matrix is diagonal and sigma, and thus also sigma squared, are diagonal. The determinant of a diagonal matrix is just the product of the entries along the diagonal. So this is given by this expression. Finally, the logarithm of a product becomes the sum of the logarithms. So in the end, we have this final expression of the capacity of the MIMO channel without channel state information at the transmitter. On the other hand, when channel state information is known at the transmitter, we can create parallel channels and do water filling across those parallel channels. This is given by this expression here. So this is just the standard water filling problem. We do a maximization of the power across different spatial streams, and this is our objective function. We explicitly encode the constraints here. As before, when the channel is random, we will have different notions of capacity, such as average capacity and outage capacity. So now we know that the capacity, in the case of channel state information at the receiver, has the following expression. It involves a sum over the non-zero singular values, and here we see the non-zero singular values squared. It is now interesting to ask ourselves, are there certain values for these non-zero singular values that lead to better or worse channels? In order to answer this question in a fair way, we need to fix the total energy of the channel. This is equivalent to setting the trace of sigma squared to mr by mt. So when the total energy in the channel is fixed, we can now look at different distributions of these singular values. The first case is when there's only one non-zero singular value with all of the energy. This would correspond in practice to a line-of-sight propagation case with only a single path. The other extreme distribution is uniform distribution of the singular values, in which case that we have mr times mt equals singular values, each with a small energy. This would happen, for instance, in the Rayleigh fading case with IID complex Gaussian entries in the channel matrix. This is the same as saying a rich non-line-of-sight environment. The capacity for the line-of-sight case is the bandwidth times log 2 1 plus an SNR, where this SNR then increases linearly with the number of receive antennas. For the non-line-of-sight case, we have the bandwidth, but now we also have the scaling with the minimum of the number of receive and transmit antennas, log 2 plus 1 plus an SNR metric, which depends on the number of transmit and receive antennas. In general, for an arbitrary distribution of the singular values with a total fixed energy, the capacity must lie between those bounds. What we see in regard to the upper bound is that this has a very favorable scaling with respect to the number of antennas. So when we put more transmit and receive antennas, the capacity scales linearly. This is extremely powerful, especially when we go to very high order MIMO with many antennas. And this is exactly what we try to exploit in massive MIMO. So now we know that in MIMO communication we want to have a rich scattering environment because this provides us with a linear scaling of the capacity in terms of the number of antennas. So a natural thing to do would be just use standard MIMO, but adding more and more transmit and receive antennas. However, in practice this does not work because the propagation environment does not provide enough richness to generate uniform singular values. In practice, only a few singular values will be available and all the rest will be zero or close to zero. A way to avoid this is by going to multi-user MIMO, where we have transmitters and receivers, many of them, each with only a few antennas. Then we can also reap these MIMO capacity gains. So in multi-user MIMO, we are trying to find a new way to create rich channels. So in single-user MIMO, the benefits from adding more antennas is low because the channel rank tends to be low, even under large antenna regime. In multi-user MIMO, we create rich effective channels through the spatial separation of users. The picture on the right shows we have a base station and a multi-antenna receiver which comprises different users. And because those users are separated in space, the channel tends to be rich. The mathematical model is now as follows. The downlink signal for user k, yk, is obtained by a signal hk xk, so where xk is a signal intended for user k, hk is a channel from the base station to user k, plus the signals intended for the other users multiplied by the same channel hk. because the channel from the base station to the user is the same channel HK plus noise. So this is the downlink communication signal. In the uplink, we have the following. Each user has its own data, xk, sends this over the channel, hk transposed, and then at the receiver, all those signals add up, and we have our observation y. Here we have assumed channel reciprocity, so we are operating in a time division duplexing mode. So downlink and uplink occur over the same frequency band. That allows us to write that the downlink channel and the uplink channel are just related to a transpose. We now study the operation of uplink and downlink in more detail. Let's first start with uplink because it is easier. We can write the uplink observation y as a large channel matrix which comprises the concatenation of all the uplink channels times a long vector which contains the transmitted signals for all of the users. The channel matrix is of dimension mr, so it has mr rows times k times mt columns. So the mr rows correspond to the mr receive antennas at the base station, mt is the number of transmit antennas per user, and k is the number of users. We see that basically we now have a standard MIMO communication system, right? Y is h times x plus n. So we can apply standard MIMO detection methods such as maximum likelihood, zero forcing, MMSE, and so forth. So for this case, we don't need channel state information at the transmitter, at the users, in order for the base station to recover the data. So this one is relatively easy, and we can use all the techniques from standard MIMO. Multi-user MIMO in the downlink is far more interesting. In case the base station does not have channel state information, all it can do is send to different users at different times or over different frequencies. So we revert back to TDMA and FDMA. If the base station does have channel state information, it can do something much smarter called multi-user precoding. It will basically send signals to all the users at the same time over the same frequencies and still allow the users to recover their signals with low complexity. The observation at user k is given as before, yk. It involves a signal intended for user k times the channel plus signals intended for other users plus noise. Now, rather than sending data in the xk itself, we will precode data. So here the sk is our QAM data, and wk is a precoding matrix. So wk times sk is equal to xk. The same goes for the other user. So the data of the other users is also precoded with individual precoding matrices. And of course there is noise. This may seem a bit complicated, but let's look at a most simple scenario where we have users with one antenna. So we will send one stream of data to each of the users. Now the model is simplified to this. Yk is now the scalar observation of user k on its single receive antenna. Sk is a transmitted QAM symbol for that user, and this is the effective channel seen by that user. It is a precoding vector multiplied by the downlink channel. Similarly, for the other users, there is interference of this form, which includes the symbol intended for the other users, their precoding vectors, and then the channel of user k. The noise is now scalar. We can now stack the observations for the different users, and we obtain this matrix model. So the observation for all users is a matrix h times w times s plus noise. This is written here in more detail: observations for all of the users, the channels for all of the users, the precoding vectors for all of the users, and the data for all of the users. So what the base station can do now is to design W, so to choose W in a smart way to optimize a certain performance criterion, such as zero forcing or MMSE. The number of users that we will transmit to can change over time, and the best K users can be selected possibly out of a large set of users in order to have a good, effective channel. So suppose we have 100 users available, we will choose maybe the best 10 to send to in order that we can design a good precoding matrix. The selection of the best users is called user scheduling. There is also a version of precoding that does not rely on instantaneous channel state information, but rather statistical channel state information, for instance, the covariance matrix of the channel. So now we should look in how we should design W in order to make life easy for all of the users. In multi-user MIMO precoding, we again focus on a simple example with k users, each with one antenna, and one base station with m antennas. The downlink channel is in a k by m matrix, where each row corresponds to the downlink channel of a single user. We consider zero forcing precoding, in which the precoding matrix is the pseudo-inverse of the channel. We should be careful, because when the channel matrix is poorly conditioned, W may be very large and we will transmit with too much power. So we need to enforce the following constraint, that the norm squared of W satisfies the total power constraint. One way to do this is by scaling all the entries in W with a low enough number such that the constraint is met. By doing this, we guarantee an equal SNR per user, which is desirable in some applications. On the other hand, we will then be limited by the worst user. We can be a little bit more aggressive by multiplying the columns of W with different scalars. And this will lead to different SNR per user. So we do the following. We take the pseudo-inverse of the channel as our precoding matrix. S is the transmitted data. And then in between, we have a matrix of square roots of powers. This is a diagonal matrix where the first entry is the square root of the power assigned to user 1. And the last entry is the square root of the power assigned to user k. We can then play around with these powers. So if all the powers are equal, we get back to the first case of equal SNR per user. We can also adjust the powers to optimize some objective function, for instance, the sum of the rates to all of the users. So here we have a generic objective function f of p. The total power constraint, of course, needs to be considered, and this can be expressed as a function of the powers allocated to each of the users. This is this constraint. Now, if f of p is sum rate over all of the users, then we find back our traditional water filling solution. A question you may ask yourself is, why didn't we do SVD? I leave this for you to think about. Finally, now we understand the MIMO capacity and the scaling with the number of antennas in a rich scattering environment, as well as that in multi-user MIMO, it is relatively easy to generate such a rich scattering environment. We are ready for our final topic, massive MIMO. While multi-user MIMO is beautiful in theory, it never worked out in practice. The reason is that to have many antennas on a mobile device is very costly. Also, when we only have very few antennas, say less than 10, the gains are relatively modest. Also, the signal processing is complex, mainly at the base station. On the other hand, when we look at an extreme case of massive MIMO, we will have one antenna per user and a very large number of antennas at the base station. The figure here shows the difference between 4G MIMO communication and 5G MIMO communication. So in 4G we have a relatively limited number of antennas, in 5G a massive number of antennas, far exceeding the number of users. And as the picture hints at, we can basically send distinct beams to each of those users. So we will now try to understand what it means to have such beams and how this leads to capacity improvements. The capacity of the MIMO channel was given by this expression. We will consider here only the case where there's no channel state information as a transmitter, in which case the transmit covariance is a scale identity matrix. Our capacity bounds are shown here, on the left-hand side for the line-of-sight channel, on the right-hand side for the rich scattering environment. We now have two cases. Case 1, where we have a very large number of transmit antennas and a channel matrix with IID complex Gaussian entries. The channel matrix will look then something like this. The number of rows is the number of receive antennas, which is small, and the number of columns is the number of transmit antennas, which is large. So the matrix will be a so-called fat matrix. Because we have complex Gaussian entries in a very high-dimensional space along the different rows, each of the rows will be almost orthogonal. This implies that an H Hermitian, which is of course a small matrix, will be a scaled identity matrix, where the scaling depends on the number of transmit antennas. This means with a very large number of transmit antennas, this will be a large number. The capacity then, we find easily that the capacity is the bandwidth now times the number of receive antennas log 2 1 plus SNR. So here MR is the number of receive antennas, which is a relatively small number, and we can also consider this to be the number of users in case each receiver has a single antenna, but there are many receivers, MR of them. In case 2, we consider the case where you have a very large number of receive antennas, and the channel is again of the same form. In that case, H will be a so-called tall matrix with many rows, each corresponding to a single receive antenna, and few columns, because we will have few transmit antennas. We can apply the same math. We find that H Hermitian H, this is different from before where we had H Hermitian, is a scaled identity matrix, a small matrix with a scaling MR that is according to the number of receive antennas. So for lots of receive antennas, this number can be very large. We apply the following matrix equality to the standard capacity expression, and we find that the capacity is the bandwidth times the number of transmit antennas and the log 1 plus an SNR. Again, this expression is in general written for a number of transmit antennas, but we could also consider this to be a number of users when each user has a single transmit antenna. So this interpretation as number of users is interesting for our massive MIMO case, but you don't necessarily need to consider this for general MIMO. Alright, so what's important here is that in both cases where we have a very large number of transmit antennas or a very large number of receive antennas, we see this linear scaling of the capacity with a minimum of the number of transmit and receive antennas. We can only reach this under so-called favorable propagation conditions, for which the channel matrix has almost orthogonal rows in case of the number of large transmit antennas, or almost orthogonal columns in the case of the large number of receive antennas. Now we go back to our massive MIMO scenario. We will change the notation slightly, so please be aware. We have a single base station with M antennas, where M is a large number, and K users, where K is much smaller than M. Each user has only a single antenna. So this is shown in the figure in the bottom right. In order to have favorable propagation conditions, we want the users to be well separated, so they see independent channels. We will use multi-user MIMO at the base station with channel reciprocity. So this means that we use time division duplexing. When the users are sufficiently far away from each other, we have nearly orthogonal channels. The H matrix, which is the channel in the uplink, is an M by K matrix. So it is a tall matrix with many rows and few columns. We will decompose the H matrix into two parts. The part D corresponds to the path loss. So this part of the channel is a diagonal matrix of dimension k by k, and this is the per user path loss. So this relates to the distance. The matrix G is the multipath fading. So this we will make as a Gaussian matrix with IID entries. It then follows that G Hermitian G is an identity matrix of small size, a k by k matrix, with a scaling of a factor m, the number of antennas. In the downlink, we have the transpose of this channel. So the downlink channel from the base station to all of the users is a k by m matrix. So this is a fat matrix with a few rows and many columns. And we find that this must be equal to the path loss matrix times the Gaussian matrix. And this Gaussian matrix is of course of size k by m. If we compute G transposed G star, then we find that this is a scaled identity matrix of size k by k with a scaling factor m, again the number of antennas. So you can verify this by plugging in these matrices. Here it's important to note that G in both cases will have IID Gaussian entries, 0 mean and variance 1. In the figure I also show the channel between a single user and the base station, and this is HI. So HI is one of the columns in the big H uplink matrix. So hi is a column vector of length m by 1. hi can also be written as square root of d, so this is the part related to the path loss, times g, a vector of length m by 1 with IID Gaussian entries. Now that we understand the uplink and downlink model, let's look at each of them in more detail. First, the easy case uplink. The observation model is of this form, where H is a tall matrix with many rows and few columns. X is a k by 1 vector containing the signals for each of the k users. We can then compute H Hermitian H, and we find that this is equal to m times d. M is the number of antennas at the base station, d is a diagonal matrix containing the path losses for each of the users. This inspires the base station to use the following combining matrix. H Hermitian times y is a small vector z of length k by 1, and turns out to be equal to the following expression, m times d times x plus w. The w has known statistics, independent across users. D is a diagonal matrix. So this allows us to write a user per user observation model, zk, given by m times the path loss of the kth user, the signal sent by the kth user, and noise. The noise is independent user by user, this is important. SNR per user is an SNRk, which is found by computing the signal power and dividing by the noise power, where we need to, of course, account for this noise variance. We find that the SNR has this expression. We can then compute the rate for the kth user by just substituting the SNR in the rate expression. We find the following rate for the kth user, and then we can add up all the rates for all of the users, because this is the sum rate that the base station will see from all of the users combined, and this is of course only the sum of the individual rates. And we see that this expression on the right is exactly the capacity expression that we could reach for this system. So this means that, at least asymptotically, for a large number of antennas at the base station, a matched filter is the best thing to do. So this means that even though we have multi-user interference, simple linear combining at the base station can lead to optimal results. In the downlink, things are a bit more complicated because the base station will need to do additional processing so that the users don't see interference from other users. The channel in the downlink is given by HI transpose for user I. Note now that this vector is a row vector of length m. The base station will do some form of precoding. So the base station will send w times s as x, where s contains the data for each of the users, so s is a vector of length k by 1. W is a suitable precoding matrix, and this is the downlink channel H transpose. N is the vector of noises seen at each of the users. We know from the multi-user MIMO slides that in general a good precoder is to do the pseudo-inverse of the channel. So here we will do something similar. We will choose a following precoder of the following form. So it will be the complex conjugate of the channel times a diagonal matrix which contains the square roots of the powers that we will use for each of the user and a scaling with the square root of m. This diagonal matrix here is to ensure that we meet a total power constraint, that we don't send with too much power. So we need to ensure that the norm squared of W satisfies the total power constraint. We find then that W Hermitian W can be written, after some steps, as dp times d. So here dp is the matrix of the powers along the diagonal, d is the matrix with the path loss values along the diagonal. So why did we go through this math? Let's look again at the observation seen by the users. So this is the aggregate observation across the different users, given by H transpose Ws plus noise. We substitute what W is. So we define W before, and we find this for W. We know that H transpose H star has a well-known expression. This is from a few slides ago. And then in the end, we find that Y is equal to this. So here, D is the diagonal matrix, dp is the diagonal matrix, and n is independent noise per user. So this means that the observation just breaks down into different observations per user as follows. So the kth entry in this vector y, we call this yk, this is the signal seen by a certain user k, is some constant, which relates to the number of transmit antennas, the path loss seen by user k, the power allocated to user k, and the signal intended for user k, plus noise. There is no longer any multi-user interference. We can then compute the SNR seen by user k, this has this expression, and then we can go again through the exercise of computing the rate and the sum rate, and we can conclude that also we have an optimal scheme. So in downlink, the match filter is asymptotically optimal. I mean here the match filter precoder. And this means that we can do simple linear processing at the base station to remove all the interference in the downlink among different users. So this is very powerful. Of course, all of this hinges on these favorable propagation conditions. Let's recap what we know so far. First of all, in the uplink, so from the users to the base station. When we have favorable propagation conditions, there is no need for any channel state information at the users, and the base station can do simple linear combining, for instance using maximum ratio or zero forcing or MMSE, in order to have an optimal sum rate. So this means that the base station can get the optimal rate even without any collaboration among the users. There is no inter-user interference. In the downlink, again under those favorable propagation conditions, the base station now needs channel state information in order to find a good precoder. In practice, the precoder can be maximum ratio or zero forcing or MMSE, and this again leads to optimal sum rates. There is no inter-user interference. This means that life is very easy for the users. They just see their own data stream without any interference from other users. So some of the benefits of massive MIMO are that we have simple processing at both the base station and at the user side. We are asymptotically optimal in terms of sum rate. Interference goes away both in uplink and in downlink, and we can serve all the users at the same time over the same frequency. On the downside, we can have increased hardware cost and increased power consumption at the base station. This is because we need many antennas, and each antenna needs their own RF chain and analog to digital converter. We have the need for channel state information at the base station. We'll talk about this later, how this can be achieved. And we also need favorable propagation conditions. In a relatively rich scattering environment, each user will have an independent channel. A question then becomes, how many antennas do we need to put at the base station to see such favorable propagation conditions? So we want at the base station side that we have the following property. Consider now a case with 10 users and m antennas at the base station. The figure on the left shows the matrix H Hermitian H visualized in 3D. We see that this is far from an identity matrix. However, when we go from 20 to 200 antennas, we see that the diagonal is approximately the number of antennas, and the off-diagonal elements are approximately 0. It is possible to compute the scaling of the off-diagonal elements as a function of the number of antennas. So we see that in practice, we would need in fact a quite large number of antennas at the base station to have these favorable propagation conditions. We can also create favorable propagation conditions in line of sight, provided we have enough antennas. To do this, we need to look at the geometry of the antenna array at the base station. Let's consider a uniform linear array where the antennas are on a line equidistant with inter-antenna spacing d. The signal from the user is arriving at a certain angle theta. This means that the signal arrives at one antenna element at some time and at the next antenna element sometime later, where this time later depends on d times sine of theta, which we will abbreviate by delta. So let's look at the signal that is received by the first antenna element. This will be equal to the transmitted complex baseband signal up to some propagation delay, an amplitude due to the path loss, and the delayed carrier. We can account for the delayed effect of the carrier in a rotation of the amplitude, so we call this g, and we can change the time basis so that we have the following observation. At the next antenna at the next antenna element in the new time basis, the signal will arrive a little bit later, delta over C, and we see this also in the carrier. We assume that we cannot see this effect in the signal itself, only in the carrier, so this effect goes away, and then we can write the exponential of the difference as the product of the two exponentials. We can now go back to complex baseband, so the receiver will downconvert. That means it will wipe off the carrier here. So then what the receiver sees on its antenna element M is an observation Ym, which is G, some complex number that's the same for all the antenna elements, the transmitted signal, and then a rotation. This rotation depends on D, on delta, also on the antenna index. Here, lambda is the wavelength, which relates to the carrier frequency and the speed of light. We can now stack all of these observations into a vector y of length m, and we can write this vector y as the transmitted complex signal times the channel, and now we also add the noise. I've also removed here the notion of time, because we don't need it. So this means that for a given user k, the channel would look something like this, right? It is a gain for that user, and then the delays across the element for that user. Each user will have a different theta k, because different users will come in, the signals from different users will come in from different angles. We see when two users have two different arrival angles, theta L and theta k, when those are sufficiently different, this product between the two channel vectors will be close to zero. Typically, the spacing between the antenna elements is about half of a wavelength. So now let's look at this product to see that this is actually the case. We evaluate here this function for two different users, k and l. We will take the norm squared because that's one real number we can plot. We can pull out the complex gains, and then in the end we end up with a summation over all the antenna elements and the difference of the signs of the angles. We call this difference delta Lk. So this is some type of metric as to what extent users are separated in the angle domain. After some straightforward manipulations, we obtain the following expression, which we visualize here as a function of delta Lk, the separation angle between the users. So here we have delta Lk. We see that when delta Lk is 0, no matter how many antenna elements you use at the base station, the function will be large. So this means we cannot distinguish between the users, so we cannot separate the signals from those users. Basically, we have no hope. When the number of antenna elements is small, let's say 10, then the function only decays slowly. So this means that for users with small delta Lk, we still will not be able to distinguish them. When m is equal to 20, the function is much more steep. This means that when the delta Lk is relatively small, the product will be close to 0 and we can distinguish the users. In other words, with more antenna elements, it is possible to distinguish users that are nearby in the angular domain. When the number of antennas goes to infinity, then any pair of users can be distinguished and the channel exhibits favorable propagation or conditions. The last topic we will cover is how the base station gets channel state information. In this figure here, we consider one coherence interval of the channel over a certain coherence bandwidth. The coherence time we call Tc, the bandwidth Bc. During this time frequency block, the base station needs to do a number of actions. So first of all, the users will send uplink pilots to the base station, from which the base station will estimate the channel and compute downlink precoders. Then we have some time for downlink transmission, and also we have later than the uplink transmission. So of this whole block, a certain time is dedicated to the pilots. The more pilots we send, the better we can estimate the channel, so this is beneficial. On the other hand, the more pilots we send, the less time we have available for data transmission. So for this uplink training, for a certain coherence bandwidth Bc and a certain coherence time Tc, we can send a maximum of Bc times Tc complex numbers over this fixed channel. If we use a fraction a for pilots, let's say 50% for pilots, then the rate that we can achieve will be, of course, 50% of the maximum rate we could have achieved if a genie told us the channel. So we want to limit as much as possible the time we spend for uplink pilots. One way to do this is by allowing all the users to send simultaneously to the base station over this coherence band. We can do this when all the users have orthogonal sequences for pilots, and then the base station can resolve all of those signals. If we have more users, what we then want to do is give some of the users the same pilots. So now let's suppose that two users have the same pilot and send the same uplink signal to the base station. Then what the base station will effectively estimate is a superposition of the channels of those two users. So this then in turn leads to a wrong precoder, which leads to a loss in rate. This in turn means that the SINR in both uplink and downlink are interference limited. So fundamentally, the fact that we have limited time for the pilots creates an interference limit for the massive MIMO communication. This effect is known as pilot contamination, because the pilots from different users contaminate each other in terms of the channel estimate. Let's revisit the learning outcomes for today. You should be able to describe the key characteristics of 5G, the differences between single-user and multi-user MIMO, express multi-user MIMO and uplink and downlink as a standard MIMO, explain why in massive MIMO users can have nearly orthogonal channels and why this is useful, and describe the effect of pilot contamination. This ends both this lecture and the entire course of wireless communications at Chalmers University of Technology. Thank you for your time and your attention.